Good afternoon, everybody. Happy Friday, and I hope that you've had a great week and that everybody's still doing good. We're looking today at lesson 30.20, which is dealing with products and quotients of functions. Pretty much everything that we did yesterday, or Wednesday, I should say, dealing with sums and differences of functions, we're going to be doing with products and quotients, but there will be a little bit of a wrinkle or a little bit of a twist when it comes to quotients of functions. But before we begin, I want to review the 4 basic operations in mathematics. I just want to make sure that you are aware of what these words mean. When you see the word sum, a sum is the result of adding things together. And I want you to note that when you add 2 items together, it doesn't matter the order in which you add them. We can pick on numbers if we like. 3 plus 8 gives you 11, and 8 plus 3 also gives you 11. We learned yesterday that when you have the sum of 2 functions, you could take f of x plus g of x, and you would get the same thing as taking g of x plus f of x. The word difference means the result of subtraction. And we know from yesterday and from experience that the order in which you subtract things matters. You will get a different result if you subtract 2 things in a different way. So for example, 3 minus 8 gives you negative 5, but 8 minus 3 gives you positive 5. And the important aspect in terms of what we're dealing with in this course is that means that when you take f of x minus g of x, that is not the same thing as g of x minus f of x. So the order in subtraction matters. The word product is the result of multiplying. And when you multiply 2 things, whether they are numbers or, as we will do today, functions, when you multiply 2 things, it doesn't matter the order in which you multiply. 2 times 8 is 16, and 8 times 2 is also 16. The word quotient is the result of dividing. So when I say we're dividing 8 by 2, we get a quotient of 4. 8 divided by 2 gives you a quotient of 4. But the order in which you divide matters. If I take 8 divided by 2, I get 4, but if I turn that around and divide the other way, I do not get 4. 2 divided by 8 is not 4. 2 divided by 8 is only 0.25. So the order matters when you are subtracting or when you are dividing. But when you are adding or multiplying, order is unimportant. There's one other thing that I would like to discuss with you before we get to the lesson, and that's that the sum of 2 things is always defined if you have 2 things to add. As long as you have 2 items that you're going to be adding, you're always allowed to add them. Any 2 numbers can be added together. Any 2 functions, as long as they exist, can be added together. The same is true of a difference. If you take any 2 numbers, you are always allowed to subtract them. And if you take any 2 functions that both exist in a particular place, you are always allowed to subtract them. So the difference is always defined. Same with the product. When you multiply 2 things, you can always multiply things as long as they exist. Any 2 numbers multiplied together will give you an answer. Any 2 functions multiplied together, as long as they exist, will give you a defined function. The problem is that a quotient is not always defined. And that's because there's something special about division. You were never allowed to divide by 0. So when you take a look at a sum or a difference or a product, you were always allowed to perform that mathematical operation. But you are not always allowed to divide. You cannot divide by 0. And that's something that's going to become important in today's lesson. Just like yesterday, we have some notation that we have to go over. When you see the product of 2 functions, it's written this way. This is saying h of x is equal to f times g of x. And what it means is you're going to take the function f of x and multiply by the function g of x. When you talk about finding the quotient of 2 functions, The quotient of two functions is written this way, and this is pronounced h of x equals f over g of x, and what it means is f of x divided by g of x. I want to draw your attention to something that's pretty important here. It's not a problem for most people, but some people, when they write things, they tend to write things quickly and it might not come out properly. That product notation is a solid dot. If you make your dot, but you don't fill it in properly, it ends up looking like a circle, and the bottom notation here means something different. So you need to know that this is what f times g of x looks like when you write it. This, on the other hand, does not mean product. It means something different. We'll learn about it later in detail. Just so you know, it's called a composition. Don't worry about what that means, but you're going to see that word again, composition. So the bottom line is it means something other than a product. Those two things are different. Now we have a domain rule. It says the domain of a product or a quotient of functions is the domain that's common to both of the functions. So this is the same idea we were talking about with a sum and a difference on Wednesday. A quick illustration of this is that if you had one function, f of x, which was defined from negative infinity all the way to positive infinity, and you have a second function, but the second function is only defined from positive 3 to positive 12, the only way you can ever add or subtract those two functions is if they both exist. And the only place they both exist is from 3 to 12, which would mean 3 to 12 would be the domain. Now that domain rule is still going to be in play when we talk about the product of two functions or the quotient of two functions, but there is an added layer to it. And it's that with a quotient, we have to exclude numbers out of the domain that make the denominator 0. Let me talk about this h of x for a second. This h of x equals f over g of x means f of x over g of x. Well, you're dividing by g of x, which means that g of x is not allowed to be 0. So any place g of x is 0 can't be in the domain. And that's why I say for the quotient of two functions, it's going to be the domain that's common to both, but then you have to pull out of that domain any values of x that make g of x, the denominator, 0. By the way, values where g of x equals 0 are x-intercepts of the graph of y equals g of x. Because an x-intercept has a particular x coordinate and the y value is 0. Let's take a look at example 1 now. Consider the functions f of x equals root x minus 1 and g of x equals x minus 2. What is the domain of each function? Well, f of x, which is equal to the square root of x minus 1, contains a radical. And we have learned in many places in high school math that the radicand, the thing that's underneath the radical sign, must be greater than or equal to 0. You cannot take the square root of a negative. You can take the square root of 0 and you can take the square root of a positive. So what we can do is we can rearrange this equation for x and get x is greater than or equal to 1. This is the domain of f of x. Now, what about g of x? Well, g of x is a linear function. It's a straight line with a slope of 1 and a y-intercept of -2. And you have learned in grade 10 math, and we've continued to use this in grade 11 and 12, that a linear function has a domain of any real number. You could write that domain instead by saying -∞ to infinity. Or we could be even more specific and say -∞ is less than x, which is less than positive infinity. We don't use less than or equal to symbols in that notation because you can't actually be at infinity. So the domain of f of x is x is greater than 1. The domain of g of x is x is any real number, which means that x can be anything from -∞ to infinity. Part B asks us to write the equation of the product of the two functions. H of x equals f times g of x means we're going to take f of x and multiply by g of x. So we're simply going to take the square root of x minus 1 and multiply by x minus 2, and we're done. There is nothing you can do with this. I suppose you could multiply that root x minus 1 through and have h of x equals x root x minus 1 minus 2 root x minus 1. But to be brutally honest with you, I'm not sure why you would want to do that. You could. It's not wrong. But usually we like to have algebraic expressions written in factored form. So this is h of x. H of x is equal to root x minus 1 multiplied by x minus 2. Now it says use the domain rule to determine the domain of h of x. Well, the domain rule says for a product of two functions, the domain is the common domain. All right, so what is the domain of f of x? Well, the domain of f of x starts at 1. X is allowed to be 1. And x can be anything bigger than 1. So this red part of our diagram represents the domain of f of x. All right, so what is the domain of g of x? Well, g of x was defined everywhere from -∞ to infinity. So the blue line represents the domain of g of x. Well, where do these two domains overlap? Because it's the place that they overlap that will be common. When you look in this region over here, only g of x exists. Which means there's no way that in that region to the left you'd be able to multiply f of x and g of x. The only place you can multiply them would be from this point all the way to positive infinity. And that domain, which is common, is the answer to the question. H of x has a domain of x is greater than or equal to 1. Now we're also asked to use our graphing calculator to confirm that. There's a number of things that we can do on our graphing calculator to actually show that that's the domain. One of them is to look at a graph. So I'm going to enter in the square root of x minus 1, close the brackets on that, and then I need to multiply that by, in brackets, x minus 2. We'll start off by choosing zoom standard. I'm going to zoom in a little bit by choosing Zoom Box. I know that the graph extends up and to the right forever, but what I'm really interested in is taking a closer peek at what's going on in this region. Now, your graphing calculator is not that good with resolution. I will tell you right now that the graph actually does start at 1. The graph actually has an x-intercept of 1, and then it extends down and up. Which means you can see based on that that the domain is x is greater than or equal to 1. You don't have to take my word for it. We can go to our table and we can see that when you're at x equals 1, the graph exists. Alternatively, you could go back to the graph and trace. You could trace 1, and when you go trace 1, you get a y-coordinate. Trace 1.05, just the number close to 1, you get a y-coordinate. But if you try trace 0.99, which is to the left of 1, you don't get a y-coordinate. So the domain rule works. The other reason why I give you this example is, even though the graph doesn't look perfect, it reinforces the idea to you that you have to be able to do things on paper because your graphing calculator can let you down. Going back to the same functions, now we want to write the equation of k of x, where k of x is f over g of x. That means that k of x is equal to f of x over g of x. F of x is the square root of x minus 1. G of x is x minus 2. And now we have to figure out what the domain rule is going to say. Well, the domain rule says that when you divide two functions, you have to start off with the idea that the domain of the quotient is the domain common to both. We've already seen that the common domain here is x is greater than or equal to 1. But the domain rule says something else. When you take a look at the denominator here, that's my eyeball, the denominator is not allowed to be 0. And if you solve this, you get x is not allowed to be 2. So even though we would normally say that x can be greater than or equal to 1, x cannot be 2. Now, how are we going to write that? Well, what we could do is just say x is greater than or equal to 1, comma, x cannot be 2. There's definitely a different way to write this, and it's to use interval notation. So instead of saying x is greater than or equal to 1 and x can't equal 2, we can say that x can be anything including 1 up to, but not including 2, in union with anything after 2, so the round brackets mean not equal to, up to infinity. And we have to use a round bracket at infinity because, as I've already said today, the idea of you actually reaching infinity is a bit of a wacky one. You cannot reach infinity. So this is another way that you could write the domain of the quotient. All right, let's take a look now at the graph of the function and see if we can confirm that when you take the square root of x minus 1 and we divide it by x minus 2, we get a domain of x is greater than or equal to 1, but x cannot equal 2. I'm going to choose Zoom 6. And now I'm going to play around with my zoom settings to give you a better picture of this graph. What you see is that the graph starts at x equals 1. I can go trace 1 and get an x coordinate. And what you also see is there's a vertical asymptote at 2, which makes sense because we've learned that when you have a denominator that doesn't cancel, you get a vertical asymptote. So x is equal to 1 or anything greater than 1, but at 2, the function doesn't exist. So our domain was correct. Number 2, f of x is x squared and g of x is root 4x minus 5. What is the equation of the product? Well, there's really not much to explain here. The product of the two functions is the product of the two functions. That's it. You multiply the two functions together. What is the domain and range of h? Well, when you take a look at f of x equals x squared, the domain here is any real number. When you take a look at g of x equals root 4x minus 5, you say to yourself 4x minus 5 must be greater than or equal to 0. When you solve this equation, you move 5 to the other side and divide by 4, so you get x is greater than or equal to 5/4. So the domain of g of x is greater than or equal to 5/4. What is the domain that's common to them? Well, since f of x is defined everywhere and g of x is only defined in a small region, the domain of h of x will be the domain where they're both defined, which is where x is greater than or equal to 5/4. That's the domain. The range, normally I would say to you, you're just going to graph this. But when you take a look at how we calculate y is calculated using this. Well, when you square x, you will always get a positive number. And the principal square root of a quantity is always positive. And what that means is that if you were to graph this, you would discover that y is always greater than or equal to 0. You know, I really don't care too much about the range. As I'm standing here looking at this, I probably, if I retyped this lesson, I would remove reference to the range. It's not important. What I told you yesterday about adding and subtracting functions is true about multiplying and dividing. If you ever really wanted to know the range, you're going to have to construct a graph. All right, number 3 gives you the graphs of two functions, f of x and g of x. These two graphs of f of x and g of x are the same as the graphs we were using on Wednesday when we were talking about sums and differences of functions. And when we said on Wednesday that we had a domain rule, that domain rule is still being applied today to products. The domain rule for sums or differences or products says the domain of the sum or difference or product is equal to the domain that's common. And where these two graphs overlap horizontally is when x is less than or equal to 4. Basically, everybody, in this region right in here, all the way up to infinity, you cannot add the functions together because they both don't exist there. You can't subtract the functions together in that region because only one of them exists. And that means you can't multiply the functions together in that region because only one of them exists. The only one that exists in that region is g of x. So the place where they both exist is from x equals negative infinity all the way up to and including 4. And we write that as x is less than or equal to 4. Now, when you have a quotient, we still start off with that common domain. Whether it's f over g of x or g over f of x, these functions can only ever be defined where the domains are common. However, we have to exclude any value of x that makes the denominator 0. So we're going to have x is not equal to as an addition to both of these domains. Now remember, f over g of x means f of x over g of x. And that means the denominator, g of x, cannot be 0. Okay, well here's g of x. If I were to say, well, what is g of x here? G of x here is 7. g of x here is 6. G of x here is 3. Where is g of x 0? G of x is 0 right here. And I mentioned this earlier, that a function is equal to 0 at the x-intercept. So the x-coordinate that makes g of x 0 is -1. So what that means is for f of x over g of x cannot be equal to -1. The domain of f of x over g of x is x must be less than or equal to 4, and there's the added condition that x can't be equal to -1. Because if x is -1, g of -1 gives 0, and you will be dividing by 0. What about part C? Well, in part C, we have to remind ourselves that g over f means g of x over f of x. And now we're looking, this is your eyeball, we're looking at the denominator and saying, well, but f of x cannot be 0. F of x is this graph. So where is f of x 0? F of x is 0 when x is 3. So if x is 3, f of 3 gives 0, and that means g over f will be something over 0, and that's not allowed. And that tells us that the domain of g over f is x must be less than or equal to 4, with the added condition that x cannot be 3. So example 4, I realize there's no example 4 in your handout, I just added it this morning. On Wednesday, when we talked about sums or differences of functions, I made a big deal that you're adding or subtracting the y coordinates. The same thing is true with products and quotients. So when I say to you f times g of -5, what that means is f of -5 multiplied by g of -5. And all that means is I go over here to -5, and I look at the y coordinate of f, and I look at the y coordinate of g, and I'm going to multiply those two things together. We're going to have 2 multiplied by 4, which means that f times g of -5 is 8. This is our answer. 2 times 4 is 8. What about f times g of 3? Well, I suppose we need to now look at an x-coordinate of 3. And we're going to read the y-coordinate of f, which will be 0, and we're going to read the y-coordinate of g, which will be 4, and we have to then say that this will be equal to f of 3 multiplied by g of 3, and that's equal to 0 multiplied by 4. When you take 0 times 4, you get 0, and that's the answer to B. By the way, you might be wondering why we're using this dot all of the time. The dot originated because if you put a multiplication symbol, if you handwrite a multiplication symbol, it's very easy to confuse it with the letter x. What about f over g of 4? Well, now what we need to do is go over to 4, which is here. And f of 4 is -1. G of 4 is 5. So f over g of 4 will be f of 4, which is -1, over g of 4, which is 5, which gives us -1 over 5. Now, what about f over g of -5? Well, we go over to -5. I've already got it highlighted. It's the one in red. And f of -5 has a value of 2. Remember, this is f, so I'm looking at the y coordinate at this point, which is 2, over g of negative 5, which has a y coordinate. Now I'm looking at this graph, and this y coordinate is 4, and that gives you 1/2. So when you are determining specific values on a graph, you have to deal with y coordinates. If it's a sum, you add the y coordinates. If it's a difference, you subtract the y coordinates. If it's a product, you multiply the y coordinates, and if it's a quotient, you divide the y coordinates. The other thing, of course, is the domain for any operation, sum, difference, product, or quotient, is the common domain, but then if it's a quotient, you have to pull out of that domain any value of x that makes the denominator 0. So there's your assignment, page 496, 1 to 2, and then 1 to 3 on the next page. I hope you have a wonderful rest of the day. I hope you have success working on this stuff. And I also hope that you have a fantastic weekend. We will talk to you soon. Take care.